Okay, in this video I'm going to talk about the sum of the squares of binomial coefficients. So basically I will show how to calculate this sum k from 0 to n of the binomial coefficient squared. So like I will show that this is equal to the binomial coefficient to n. So basically, to give a little background, so in one of the previous videos I showed how to calculate the sum of just the binomial coefficients without the square. So like this sum, basically I showed that this is equal to the power n. And in another video I showed that we can also calculate the sums where this binomial coefficient is multiplied by the power of k. So k like this from 0 to n, also k squared, also k cubed, and so on. So for basically for an arbitrary power of k to the power s, we can, like, there is a way to calculate these kinds of sums. So so it is kind of natural next to wonder what would be the sum of the squares of the binomial coefficients, and it turns out that it's possible to calculate it, and it is a kind of a short expression. It's not some kind of long expression in the answer. So so let me remove all of this. Okay, so let's prove this. So for the proof we will use the van der Mon's identity, which I proved in the previous video. So the van der Mon's identity, so let's write. So van der Mon's identity, right? So it looks like this. So the sum of the product of two binomial coefficients where I plus j is equal to k, this is equal to the binomial coefficient m plus n k. So this is true for any m and k, right? So this is the van der Mon's identity. So now what we do is we set, so like you see that we want to have a sum of squares of the binomial coefficients, and here we have a product of two different binomial coefficients. So the idea is to select m, n, and k in such a way that these two binomial coefficients would be equal to each other. So and it turns out that it's possible to do. So basically we select, so m is equal to n and is equal to k. So all three of these parameters we select equal to each other. So let's use the variable n for all three of them. So so then the van der Monte identity becomes this. So the sum ni and j, the sum for all such I and j such that their sum is k. So I plus j is equal to k, and this should be equal to n plus n would be 2n, and k is also equal to n. So that's what we have. And now to evaluate these two binomial coefficients, like they are actually equal to each other. And to see this, we simply observe that yeah, by the way, k, like instead of k we need to write n, because k is equal to n. So observe that like what is, so like by definition, right? So what is n I? This binomial coefficient is n factorial over I factorial n minus I factorial. So you see that this expression, it is symmetrical around I and n minus I, right? So if we replace I with n minus I, so like if you write n minus I, this binomial coefficient, so it would be equal to n factorial. Here is n minus I factorial, and here is n minus I, right? Factorial, like this. And this, of course, this expression, of course, is equal to I. So this whole expression is equal to n minus I factorial, and this is exactly equal to this expression. So exactly equal to the binomial coefficient ni. So we can, in the binomial coefficient, we can replace I with n minus I, and the value would be the same. And so here it's exactly like this in this sum. So I and j, their sum is n. So basically j is equal, so from this j is equal to n minus I. So this sum can be rewritten. So this sum can be rewritten as the sum by I as ni and n minus I, right? Because j is equal to n minus I. So like this condition, we can simply rewrite it with one index in the sum. So and because of this, because this binomial coefficient is equal to this one, these two are just equal to each other. So this is equal to the sum by I and I squared, and that's what we have. And we can replace the index by k just for convenience to have it the same as in the problem as in the statement, in the original statement. Here we have k, so we can, instead of I, we can write k from 0 to n k squared. And I, by the way, here is also from 0 to n. I didn't write it, but it's kind of assumed. Yeah, so this expression is exactly so this is equal to this, right, by the chain of equalities, and this is exactly what we need in the statement. So this concludes the proof.